features like this. And you
Hello. If one Spanish, if one if one పెట్టిన సరే ఫోన్ ఆఫర్ చేయకపోవాలి ప్లీజ్ మీరు నా ఫోన్ చేసిన ఫోన్ చేసి నచ్చిన
and if the model F gets it right, it does not add any penalty.
దీనికి కనెక్ట్
It
చేయాలి.
simply adds zero. That's a simple counting loss. It's a zero one misclassification. However, this particular misclassification loss, which is in fact a very good loss in terms of a lot of properties, and that is what we would want to ideally optimize. It is not numerically amenable for,
ఇది
sorry, it is not amenable for optimization in to solvers. That is because it does not have certain properties that make certain functions easy to optimize. So we have approximations like the logistic laws or the hinge laws, and these give us different models. With modeling, you also have tell you how good or bad the function is on a given data set D. And what we are doing here is computing this loss on each of the samples and summing it up on the training data D. And then we want which minimizes this objective function. The function pay a penalty of 1. And for all those where there are no mistakes, they make it makes the function pay no penalty. So it's roughly just counting the number of mistakes it's making, the model is making on the training data, the fraction of the sample where it's getting it wrong. But then, like we discussed, this is a loss function that is not easy to optimize. It is not a loss function that can be uh, where you can solve for the parameters w easily. that you could add.
Hello.
It gives you algorithms by similar results
Hello.
very similar to the lasso algorithm. What it really does is it tries to push uh, small and in determining or in making a decision. That's what your L1 regularization does, and L2 does something a bit different. It's not as aggressive as the L1 regularization. It won't force them to zero, but it kind of does a uniform reduction in coefficients in all your coefficients involved. And by choosing an appropriate lambda, you can ensure that your model has the right complexity. It's neither overfitting or underfitting. So regularization is what you would use uh, to ensure you're fitting right and not overfitting or underfitting. Right. But how do you quantify a poor fit? What are the variables that you would use to determine uh, whether a particular fit is a good fit or a bad fit? Let's say we have a million data samples in our training data, and build a model M1 by drawing a random sample of 200 instances from the million samples that you have, and learning a model on top of this 200k samples. So you're just sampling 200k uniformly and randomly from the 1 million samples that you have, and you're fitting a model to it, a linear model, just like we have seen. It's you in the uh, predictor function. Let's say it's a linear function f, and you determine the loss function. Let's say it's a square loss. Let's say you're using regression, it's a square loss. And you fit a model. So you get a model M1 or a model F1, let's say. Um, Now repeat this process. Draw another sample of 200,000 from this 1 million and fit another model F2. Repeat this 10 times and you get 10 different models. Now, let's say you receive an unseen 1 million. It's a test input. It's a new input that you get. And you have to make a prediction on this input. Models to make 10 different estimates the value of the prediction. Okay, so you have got 10 different estimates from your 10 models on this unseen sample. What are the ways that can, various ways in which these 10 predictions or 10 estimates can look like? The best case is you have these 10 estimates very neatly and tightly clustered together, and they are very close to the ground truth, which is the true value that you're trying to estimate. These concentric circles that you see, they are the distance from ground truth. At the center of these circles is the truth, and these crosses that you see are the estimates from your 10 different models. And what you see at the left bottom is the best case scenario. Estimates is very close to the truth, and all your estimates are tightly clustered together. That's really the best that can happen. So you have what is called low variance, which is the spread in your estimates, and low bias, which is how how far you are from the truth. Now, what is the worst that can happen? It's the right talk. They are really spread out very far. Your estimates are very far from each other. That's high variance. And they're all far from truth. That's high bias. And what are the other two scenarios? You have low variance. They're all tightly together, but it's got a high bias. You're far from the truth. And the other case, of course, is you have very high variance, but you have low bias, which is to say, uh, they're all spread out, but they're spread out around the true value. Now, your overfitting and underfitting are really just cases where you have high variance and high bias. So, overfitting is where you have very high variance because, like you've seen in the high polynomial that we have fit to uh, uh, linear data drawn with some random noise added to a linear function. You are fitting even to the noise, and hence you cause high variance there. On the other hand, underfitting is where you fit a model with complexity lower than problem of very high bias. Important uh, statistical components that you would use to determine whether your fit is good or bad. While these are the statistical quantities that you would use, you cannot always compute these in practice. So, how would you determine in practice if a particular fit is a good fit or a bad fit? And this is how you would really do it. Given any data set, you would split it into training sample and test sample. And these are distinct samples. So none of the records or instances from your test sample would appear in your training sample. They are distinct samples. And in training the model, which is in learning your model F star, you would only use the training sample. You should never use the test sample. Train on the training sample, learn a model, and then use the performance of the test sample to determine if it is good enough or not. So this green curve that you see is the error on the training sample. And the prediction error is a function of the bias and the variance. If you have very high bias and very high variance, you're going to make a big error. You want both bias and variance to be low. But when that is not possible, uh, you trade off one for another and ensure